Right. So what we are going to study in this particular 6 lecture series is surfaces. Okay. And these surfaces we are going to consider within R3 only. So we can see it with our eyes, because beyond 3 we can't see it. And as many of you are familiar with these things, right? We know what is a plane is. So can anybody tell me what is the equation of a plane, or how you realize plane as inside R3? Inside R3, can you tell me what is equation of plane? How you determine plane? Do you know actually one of the example here? Yes.
Equation of a plane in R3 is in the form ax plus by plus cz plus d equal to 0.
Yes, that is correct actually, or let us write it like this. Very good. So that is how we actually see. Can you see this, or it is too less small font? Ax plus by plus cz is equal to d.
It is visible.
Right. So plane is given by this equation. This is a linear equation, and of course it is a linear equation because we know that plane is something which is a flat thing, right? Yeah. So this is actually is a equation of a plane, and we are going to study the surfaces. Surfaces means what? Actually it will be something which is like a plane, and plane is example where actually everything is a flat. Okay, there is nothing curvature, nothing is there. Okay. Another thing is actually about a sphere. Sphere is the one which, you know, what is the equation of sphere? Can you tell me?
X square plus y square plus z square is equal to 1.
Yeah, right. So if you take actually, this is an example of a unit sphere, right? But again, if you look at a sphere is this one. Can you see this? So if you look at a sphere, see, sphere is not a flat, right? I mean, if you look at it globally, is it a flat? Globally, I'm talking about.
No. No, it has
curvature. Right? But right, but it is a surface. We will see actually why it is a surface, because if I actually really zoom in, what will happen is it will suddenly start looking like as a flat. Like for instance, Earth. When we walk on the Earth, we don't feel like we are walking on the ball, but we feel like we are walking a flat. And similarly, there are other examples like cylinder is there. So cylinder also, all of you are familiar with cylinder because we see them all around us. And we again, if you look at cylinder, it is a circular. But when you are locally, so cylinder means what? Actually, we are assuming its walls are there. Okay, these walls are there, and we are not assuming inside part is not there. Okay. So cylinder means just what we are looking at is we are like taking a say what we are doing is we are taking actually a sheet of paper, and then that sheet of papers we are actually we kind of paste there these edges, and what we got is actually a cylinder. So not a, it is a hollow cylinder, and that is also example of surface, because so those kind of objects which we are going to study it. Okay. And something which is here actually if I want to make a cylinder, what I'm doing is I'm actually pasting this wall to wall. But if I actually take a sheet of paper, and instead of pasting this line, I can just paste in a opposite way, and then what I get it is a Mobius strip, right? All of you must be familiar with these surfaces, and these are the examples which are surfaces which we are going to study it. Okay. But there are some other surfaces which you might have heard, like for instance now, can you give me any example which is not mentioned here and which you will be keep on hearing? That topology, you said that you know topological manifold. So can you give me any two-dimensional topological manifold which I did not listed here, which is very commonly used?
Torus.
Okay, torus actually I mentioned here, I did not say it, but torus is also a surface which we are going to do. But there is one more thing which is a projective plane. Have you heard of projective planes?
Yes.
Yes. Right. Or another thing actually we were talking about was which number theory people would certainly know is actually a upper half plane with a closed upper half plane, right? Have you heard of them? Actually, they do a lot of number theory is done in closed upper half plane, and actually geometric people will be always talking about RP2, right? Have you heard of this thing? Real projective plane and closed upper half plane?
Yes.
Right, but we are not going to deal with them because of the following reason. Because real projective plane, you cannot be embedded inside R3. Okay, so you need R4 to put it inside. So we are not going to talk about such a kind of thing. We will be only talking about those surfaces which lies within R3. Okay, so we are going to talk about something which just we can embed them. Embed means what? Actually, you can visualize them. You can consider it as a subset of that R3. Those are only we are going to talk about. Okay. And what is the key idea for making this spaces is, what you do is you take actually you take these open sets from the plane and then you glue them together in such a way that we will get a geometric object without a boundary. So why I said without boundary is because we don't want to deal with such a kind of things. Okay. So I don't want to consider upper half plane where actually we have a closed boundary. So these boundary points are there. They are very interesting, but unfortunately, it is not a part of our syllabus first place. So we are not going to talk about it. Okay. But they are also very interesting. So right now what we are going to do is we are going to stitch or glue our open subset inside R3. We will take a open set inside R2, then we will glue them together and we'll put them into R3. Those kind of things we are going to talk about. Like for instance, suppose if I take this kind of a disk inside, which is homeomorphic to disk inside R2, then you take another disk and then you stitch them together to form a sphere. Okay, those kind of things we are going to look at. So that's what we are going to do. Okay. Now actually so one thing about this is you have all of you. So what do you mean by gluing together? Or if I have something inside R3 but I want to look at it like R2, so what is the meaning of this thing? So have you studied parameterized curve last week, right? Professor Shastri must have taught you. So what is a parameterization of curve means?
It's a map from interval to R3 or R2.
Right, exactly. So when you do these curves, what we do is these curves, they may lie inside R3, but we know that they are curved, right? So in that case, certainly they should be coming from the line, somewhere from R. And then actually what we do is we give them a map here and then we say that that is a parameterization, right? So and if you look at inside R3, remember that inside R3 we have a 3 coordinates, right? So what is a parameterization means? Each of these coordinates should be dependent upon T, right? That is how you studied this parameterized curve. But now what we are trying to do is surfaces, right? So surfaces is a two-dimensional object. So if I have a two-dimensional object, how actually we can embed inside R3? Suppose if I want to take actually a two-dimensional object, and if I want to put it into three-dimensional object, what should be a parameterization? How parameterization will be dependent? Will it depend upon only single object thing, or it will be depend upon more than one variable?
It will be two variable.
Right, that is correct, because this is a two dimensions, so certainly the two words should come. So what is this, all these surfaces and so on, which we are going to study now, is what will happen is you will have a two parameterized parameters will be there. Either we will denote it by UV or we will denote it by XY, and then they will be give me a function, like the first coordinate will be function of UV, second coordinate will be also a function of UV, and the third coordinate is also going to be a function of UV. Okay, so this is called parameterization. So it is a clear-cut generalization of a parameterized curve. So what we are going to do is, so let me just read this thing and then I'll tell you. So in the first week, you have studied parameterized curve, and now we are going to study the functions of two variables. Okay, now this is u and v, whatever I wrote it, they are two variables. And what we are going to do is we are going to define them in this way. So that is what is our job is to give now. So if I have a set inside R3, so suppose for instance, I have this sphere inside R3, what I have to do is I have to give a map, phi map from the open subset inside R2 to open set inside R3, and that will be precisely look like this. Each of these three variables x, y, and z, they will be dependent upon u and v. Okay, so that is called a parameterization. We will make it more we will make it more precisely later on. Okay, so this is a one way of looking at it. So what is a surface means? It is a parameterized, locally parameterized to parameterized by the two variables. Okay, so that is how you can look at. Another way of looking at a surface is what actually one of your friends said, Swaroop said, it is locally flat. So what do you mean by locally flat is, it is just like Earth. So if you see Earth in the very small neighborhood, like if you just look at it as with your eyes, wherever is your horizon is going, then in that place it looks like a flat, right? We don't when we ride a bicycle or when we walk, we don't feel like there is a curvature, right? It is really a flat surface. I mean, forget about mountains and so on, I'm not talking about that, but otherwise it is actually a flat thing, right? So it is like this. If you look at actually, so all of us can actually walk on this earth because locally it is flat. But suppose, and why actually we can walk on the earth is because we don't assume it to be a ball, right? Otherwise you will be juggling with even walking on the earth. It will become very difficult. But thankfully our earth is locally a flat. Okay, so these surfaces you can actually imagine, like if we are not talking about a global, but we are going to look at only locally where it is flat, exactly like R2, and we can walk on that. Okay, that is how you should feel about surfaces. Third thing about, but still actually what we know that we have this, I mean, but surfaces are not all that boring. They are not just like plane. It is more to that. So you have some kind of a curvature to each of these surface. So globally, locally, they are flat, but globally, they are not flat. So they have some kind of a curvature. So now actually when we are curving something, we should have some kind of quantity to it. You can't curve whichever way you want and we will get a surface. Like for instance, suppose if you take this sphere, this curvature is okay for us. But suppose if I take this line and actually I curve it, and then look at here, what is happening is this circle is pinched into the point. So such a kind of thing is not a surface. So we will actually make our definition precise why this is not a surface, because we are punching here, or because and this is why it is happening is, I'll give you, in fact it is one of our we will prove this fact. And another thing is also not okay, because we are planning to study something called smooth surfaces, right? I mean, you must be already known about it. So we are not going to talk about just a topology. We are also going to talk about something which is called smooth surfaces. So now, can you tell me, can you give me a continuous map which is not differentiable, which we study in 11, 12 standard and so on?
Mod X.
Mod X.
Yeah, that is, yeah. So one thing that is very good actually. So that's what I was thinking about. Mod X is I mean, one second, let me, this x-axis and y-axis, let me make it. Yeah, so whenever actually if I say you that, okay, a function is not differentiable but continuous, what comes into our mind is mod x function. But now we are talking about surface, so we don't want a one-dimensional object. I want a two-dimensional object. So let us make this into a two-dimensional object. Anyway, we have one more extra dimension is left with us, right? So you can actually consider as a paper, you consider it as a paper, I mean a plane which is folded. So this is like a folding plane. Okay, so if you look at here, what will happen is, if you look at actually individual all these points, it is like a flat only, right? Because it is exactly like plane. Are you convinced by that? If you look
Yes, ma'am.
at any, right, but if you look at this particular part, which is this folded edge, there actually there should be a problem, because we know that, at least we know that in usual thing, mod x function is not a differentiable. So this is kind of thing is called a folding plane. This kind of thing is called pinch point. So these kind of things we have to avoid when we are constructing a smooth surfaces. Okay. So this is actually what we are going to study in today's and tomorrow's class. Okay. So first thing is, what we are going to do is, we will, I'll talk about what do you mean by gluing, or what do you mean by parameterization, or what do you mean by this quantifying, or these kind of things. This is also called regularity condition. Okay. So in these two lectures, we are going to formally, I'll define all these things. Okay. So is this fine so far? So far, are we good? This is just a motivation part. So even if you're not familiar with some concept, I'm okay. But is this motivation enough for you?
Yes, ma'am.
Okay, yeah. Does anybody have some doubt or something? Then I can actually address. Okay. Priyanka, is it okay so far?
Yes, ma'am. Yeah.
Okay. Right. So now actually let us look at formally we have to define all these things, right? So I have to give you a definition. What do you mean by what is the surface is? And first we will give a definition of topological surface, and then we won't call it topological. We will just call it as a surface. And then later on, what we are going to do is I'll give you a definition of smooth surface. Okay. Right. So as one of your friends said, locally it should look like R2. So what do you mean by locally it should look like R2? All of us are familiar with what actually we know what are the what is the because we are talking about topology, we are talking about continuous map. And if I want to say that it is looks like a R2, that means I should give a homeomorphism from R2 to my to some neighborhood of a surface. Okay, that is what we have to give. Now the one thing is that, let me just recall that part. Suppose if I have R3, R3 has its own topology, right? What is the topology on R3, which is a standard topology? What are open subsets of R3? I mean, or what are the basis for R3's topology?
Usual topology, open spheres.
Yeah, open spheres will give me actually topology. That is correct. So now actually, but these surfaces are two-dimensional object which are lying inside a three-dimensional object. So suppose this is my surface S, and now actually I want this to be a two-dimensional object. So is two-dimensional object is can it be open inside R3? Is sphere open inside?
No, no.
No, right? That is correct. But I think one of you are trying to say this. So in general, what happens is I can assume that all of you know point set topology, right? So let me just quickly say that, because see, I was trying to follow the book which is given to us, which is a reference book. So he is talking up like this. So I'll just give you, because I don't want to actually, I know all of you know point set topology. So we can assume that, right? All of you know point set topology, right?
Yes, ma'am.
Right. So now actually, so when A is a subset of X, where X is a topological space is there, then we define something called subspace topology on A, right?
Yes.
We define subspace topology. So what is subspace topology means? Any subset F contained inside A is open if and only if. Can you complete it?
F equals to some open set, intersection of some open set in X with A.
Right, that is very good. So U is open in in X. So that's what we are going to do is, so if even if my sphere is inside R3, it is, so what are open subset of spheres will be, you take an open ball, or I mean, it is a union of all these things. So I'm just talking about the basic open set. So you take an open ball inside R3, intersect with that sphere, and then whatever you get, that is actually going to be, so it will be like, suppose, I mean, I think many of you play the cricket and so on. When your cricket ball actually, when it gets a, I don't know whether you people nowadays play with those rubber red color ball. So when we were kid, that time they used to play, and whenever it used to break, it will break like some disc kind of thing, right? So that is precisely going to be open subset inside R2 if you intersect with this open ball inside R3. So those kind of things are going to be open subset of R2. And then of course, we know that open subset means you can take a union of open set, intersection of open set, and then whatever forms, those are going to be open subset of S2. So what we want to do is, same thing we want to say it here. So what we are going to do is, a subset S of R3 is a surface if for every point P belongs to S, there is an open set U in R2 and an open subset W in R3 containing P such that S intersection U is homeomorphic to U. So this part actually we can, if you know this, let us just forget about this part because all of you know that. So in fact, we don't even need to write these things also. We can, what we can say that an open subset U in R2 and an open subset some U prime in S, which is homeomorphic, or whatever is homeomorphic to U. Okay, so just to consider like this. For every point P, what you have is, for every point P, I'll have a neighborhood of this P inside S, which will be homeomorphic to some open subset inside R2. This is my R2, okay? So sigma, this is a map from open subset inside R2. So this is U is an open subset inside R2. From there, I'll have a map to S intersection W, means this is an open set in S, and you have a homeomorphic. So when you look at S intersection W, this is homeomorphic. So this is going to be a two-dimensional object only, okay? It is going to be a two-dimensional, right? And then actually how your sigma will look like, this is a map from 2-dimension to 3-dimension, right? So I have this coordinate U and V. So sigma of UV, it will look like as a X of UV, comma Y of UV and Z of UV. So this is that parameterization which I was talking about, okay? So this is that parameter. So it is exactly like how you see how you learn the parameterized curve. So this is also similar to parameterized curve. Okay. So for what we are doing is, for every point P, or let me write this as a Q inside S, you can find the open neighborhood of Q inside S. Neighborhood U in S, such that it is homeomorphic to open subset of R2. Okay, that is what is the definition. So if those who know already what is topological manifold, for them this definition is the same. Okay, so this definition is much more simplified definition because he's not even talking about subspace topology. Okay, is this clear to you, this definition? Do you want me to read it again?
Can you explain once more?
Okay, I'll explain to you once. Okay, that is good. Yeah. Okay, so let me just start with a clean slate. See, what we have is, we have a so what you have is, you have this surface S. Let me draw just a sphere because it is easier to draw, but it may not be a sphere. Okay, I mean, it will be some surface. So it is a two-dimensional object. Okay, so some surface. Okay. And I want to, I mean, some subset. So S is a subset of R3. Okay, that is what is given to me. And I want to give you a definition of surface. So what is the definition is, you start with a point P belongs to S. Okay, so my P will be somewhere in this. Okay, so for this P, there should be, so there exists a sigma. This is a map from U to S intersection W, let me write it, where W is open subset. So for point P, what you have is, first I'll get a U contained inside R2 open subset, okay? So requirement is, we have a three requirements are there. One is open subset of R2. Second is open subset of R3. And a homeomorphism. You know what is homeomorphism is? Homeomorphism means a map which is continuous and it's
Inverse is continuous and bijective also.
Right, exactly.
Bijective, inverse is continuous and continuous.
Right, very good. So this is a homeomorphism, is you have a continuous map which inverse is also continuous and map is a bijective you need because inverse should be exist. So for every point P, I should have these three things. Okay, that is what is the definition of surface. If you want to draw a diagram, what we have to do is, so here actually we are inside R3, but we have to go inside R2 because this open set U, this is inside R2. Okay, so this is my U here. Okay, so this is my U which is open in R2. See, if I use the same X, in general we write X, Y, Z, sorry, actually, I should write this as a Y. See, in general, what happens is we write XY coordinate for R2, but now actually we have to deal with the R2 and R3 separately. We will write coordinate for R2 as a U and V. Okay, so this is exactly like X and Y, but I just denoting it by U and V. Okay, and then what I'm saying is you have this map sigma. So where sigma is going, if you look at the image of sigma, that will be somewhere here, right? So we are saying that image of the sigma of U, that should be homeomorphic to, this is not a notation, okay, this is homeomorphic to S intersection W. Okay, so if you look at say okay, so if you look at a sigma of U, that is going to be S intersection W because this is homeomorphism, right? So this should be a surjective map. So sigma of U should be S intersection W because we are telling that this is going to be a homeomorphism here. Okay, so for every P, I am giving you these kind of a data. Okay, for every P, I have this data. So what data I have? A sigma I have a U and I have a S intersection W. Is this okay?
Yes, ma'am.
Yes, ma'am.
Okay, good. Okay, so this we are going to call it as a surface patch. Okay, we are so far I did not give you a definition of topological manifold, but this data, this is called surface patch. Okay, so this is called surface patch, and if you can find surface patch for every point on S, then we will call it as a surface. Okay, so for every point you should able to find this sigma U and W such that these conditions are being satisfied. Okay, so let me just read the definition. Okay, so a homeomorphism sigma from U to S intersection W, as in the definition, is called surface patch or parameterization. This is also parameterization, right? This you can can you recognize this with your parameterized curve? Can you see the similarity? Can you see how parameterized curve, and these are actually a parameterization because there actually in a curve means it will be only T was there, and now actually here I'll have a two parameters U and V. Is that okay?
Yes, ma'am.
Yes.
Okay, right. So so this is actually a definition of surface patch. A collection of such a surface patch whose image cover the whole of S is called atlas. Okay, so what we do is we will call actually all these things as atlas if it covers the whole of S. So collect for each of this point one surface chart and collect them together. This is called atlas. Okay. And our job is in fact today what we are going to do is we are going to find atlases for various surfaces. Okay, that is what we are going to do it. Okay, so let us so this definition of surface is clear to you actually. You don't worry about this what is it, scribbling over here. I'll give you a clean notes in which all these things won't be there. Okay, so let us see examples now. So suppose a plane is given to me. Can you prove that it is a surface? So what is given to me is plane. So just now, one of you told me that what is the equation of plane is? Sorry, C times Z, we write it. Right, so this is actually this is equation of plane. So all those points x, y, and z belongs to R3, such that ax plus by plus cz is equal to d. This is plane, and I want to show that this is a surface. Right. So how to, can you give me a, so if I want to say that this is a surface, what I have to do is I have to select a point from my plane, and then what I have to do is I have to give some homeomorphism. Or another way of doing is actually what we can do is we can give one surface patch which will cover those points. So since plane is a flat, we at least do you think that we can cover it with a one single patch, surface patch? What your intuition says?
Yes, ma'am.
Can
Yes, ma'am.
right, now we can give directly homeomorphism from R2 to R3. So can you give me a homeomorphism? Let us assume one condition that C is not equal to 0. Then so we will just study the case when C is not equal to 0. You can study the other cases later. So can you give me a homeomorphism from R2 to plane, which will essentially cover the entire, so homeomorphism when I'm writing, that means it is covering the entire plane. So can you give me that? Priyanka, can you give me what is your,
Ma'am,
what do
I
you
was
think?
thinking, can we take just the projection? Like in the, we will have a plane, right, in R3. So we'll just project it on R2.
Yeah, but now actually that is correct. So you want to give that homeomorphism now, but we have to give a surface patch. What is surface patch, Priyanka? Tell me. See, we have to use that. Whatever you are saying, now we will use that. But when I say that for a surface patch, that means you have to give a map from R2 to P. So can you give that reverse map for that projection?
xy goes to x comma y comma d minus ax minus by by c.
That is very good, extreme, very, very good. Priyanka, do you understand? Essentially, this is your
Yes.
projection. Is if you look at its inverse, it is going to be a projection only. But remember
Yes.
that when we are talking about surface patch, now always try to give a map from. I mean, in fact, for surface patch, we are saying that U is an open subset of R2. So give me a map from there to there, okay?
Yeah, you, ma'am, we are taking here R2 only, right? The one thing only.
R2, exactly. So
For all
actually,
P.
we know that. Yes, that is correct. See, this P is a capital P. Okay, so let me just write it like this. Okay, just to make sure that this is not a point, this is everything. Okay. So see now if I want to give a definition like that, suppose if you take any point x, let me call P naught is equal to x naught, y naught, z naught. Can you now give me that surface patch? What your surface patch you will get it? You will give this surface patch, right? Maybe I should make a, let me just, what I was trying to say is, see, if I said here that for every P, I should give this homeomorphism. So suppose if I pick up a point inside the plane, then which surface patch I'll give it? Suppose if I pick up this point, what sigma I'll give?
Ma'am, the same sigma.
Exactly. So same sigma will work for every point inside plane. So that means what we have done so far is, so what is the at last here? See, atlas, do you remember definition of atlas? You have to give a surface patches which will cover the entire S, right? This is my definition of atlas. So here atlas is consisting of only single surface patch. Okay. So this is also atlas for P, which consisting of only one patch. Okay. Is that okay?
Okay, ma'am.
Yes, ma'am.
Right. So now actually let us look at another example. So this plane is something which is a simple example. Then another example is say a cylinder. So can you So now suppose we have a cylinder. So for cylinder, what you can do is, do you see whenever we say a cylinder, can you recall something actually when you do in the calculus? What is, whenever you have a cylinder, what comes into your mind actually? There are these cylindrical coordinates are there, na, which you actually use it to integrate this. If you want to find some kind of surface integrals and so on, what you used to do is you used to do cylindrical.
R sin phi cos theta R.
Yeah,
That
is
is
okay.
spherical.
Okay, I did not hear what she's saying, but you remember that word at least, right? What is that? Cylindrical coordinates.
Yes, ma'am.
Right. So, okay, I did not hear what Devi said. Let us see actually. Anyways, what is it? Okay. So, do you remember?
Circular is like R cos theta R sin theta. If you use sin phi also, then it is cylindrical.
No. That is a spherical, Devi. Cylindrical
Okay.
coordinate. See, what is a cylinder? You tell me, Devi. Cylinder is like this, right? So, what is the Z coordinate is? See, if you take any point on the
Z is Z itself.
Exactly. So you don't need that, what is that, cos phi or whatever you are saying, right? That we don't need it here. That one theta will be enough, right? Because Z is Z
Yeah.
only.
R
So what?
cos theta R sin theta and Z.
Uh, yeah, so let us take R is equal to 1. Okay, let us fix this. And then actually what we can do is, and we are taking an infinite cylinder, okay, not a finite cylinder. We are taking infinite cylinder. So what are these coordinates are actually here theta comma, let me write it as a Z because our last coordinate is Z. So let me write it as a Z. Then what will be your cylindrical coordinates are?
R cos theta, R sin theta and Z.
R is equal to
R
1.
is
So
fixed
One,
here.
so cos theta, sin theta and Z.
That is correct. Very good. So we have this cos theta, sin theta and Z. These are actually a cylindrical coordinate. So for cylinder also, if I want to give a surface patch, what I'm going to use it? I'm going to use the same this cylindrical coordinates. So can you use a cylindrical coordinate to give me a surface patch on this cylinder? Okay. But one thing about this, is this an open subset of R2? See, this is a subset of R2, that is okay. But is this open subset?
No, ma'am.
No, right? It is
No.
not an open subset. So that means, because, so can you make this open? So suppose because I need to give a map from open subset. So let me write it as a sigma. How to make this open? See, R is open. It is a product
Just
topology,
0,
right?
2 pi, 0, 2 pi open interval and then.
Yes, that is correct. So if I want to make this open, what I have to do is I have to open this close brackets to the open bracket and give a map over here. So now, but now, is this going to be homeomorphism with a cylinder?
No, ma'am. One line is removed. Like,
Yeah. So which is that line which will be not counted here? What are those points?
one like x comma. Sorry, x is fixed here. So yeah, correct. 1 0 Z.
Right, 0 Z. So that is this is the line. This will be entire line, right? And this Z belongs to R. So this entire line L, that will be missing from the image, right? But it is okay, because what we know about surface patches, we don't need to talk about only one surface patch. We can have another surface patch to give the other side. So this actually, except for this, so S minus this line L, that will, all those points will be covered by this surface patch. Is that clear to all of you?
Ma'am, can we take from 0 to 3 pi?
See, if you take a 0 to 3 pi, you tell me actually what will happen is, suppose if I take a 0 to 3 pi, is it going to be a bijection?
No.
No, right? Your point is correct, but we need a bijection. This, what will happen here? Here, injectivity will be loose, right? So we cannot
Yes, ma'am.
actually take till 3 pi, right? But one thing you can do, na, because see, we don't need to fix to a one surface patch. So can you give me another surface patch, for sigma prime, for instance, from another? So here actually you are talking about that 0 to pi, right? So even you can take it from minus pi by 2 to pi by 2 cross R2, same map you can give, right? And then can you cover the other part of this, whatever is its image? So let me call it as a U prime. So if I take this, is this open subset? Same map you give.
Yes, ma'am.
Right, so it will now actually what will happen is this line L also going to be inside this image, and together both of them will cover the entire cylinder. So you can take a sigma, I'm not writing now these things, but sigma prime, this will be atlas, right?
Ma'am,
Is that okay?
Ma'am, that's fine. But the sigma prime, that will be like just covering the right half of the cylinder, right?
But that is also okay, na,
That's
Priyanka,
okay.
because
Yeah, that's fine. I'm
yeah,
just
because
okay.
yeah. So if you want, actually, you can make it bigger also. If you want, actually, what you do is, see, you just take it like this, right? Minus pi
Yeah.
to pi.
Mhm.
Okay. See, surface patch means atlas means what? Union should cover it. So even if you, in fact, don't need to even go minus pi by 2, na, you can even go very epsilon neighborhood of that 0. That will also do for us. Okay.
Yeah.
Because we just need cover. Yeah. So now actually one question to you, can you cover the entire cylinder with a one patch? Is it possible? See here what I gave you a cylindrical coordinate, and then what I did was I gave you a two patches, because with a cylindrical coordinate you cannot have a one single patch. There is a all of you actually know about that what you call that uh, all of you know winding numbers and so on, so you cannot anyway give the bijection anyways with this. So cylindrical coordinate will have that singularity if you try to close it. So now my question to you is, can you give another way, another map, so that can you cover the entire cylinder with a one single patch? Is it possible? See, I'll just give you an idea. You have to write it down. Okay. So what you do is, you can actually do that. So what you do is, you just take uh, disk. Okay. And what you do is remove this 0, 0 from here. What we have done it. So what I have is, I have this open disk minus what I'm doing is, I'm actually removing 0, 0 from here. So now actually what we are going to do is, so here, what a cylinder is made up of, right? You have a lot of lines which are close together in a circle, right? See, what is a cylinder? Now you take a line and you rotate it around a circle. Is that a cylinder? You know that rotating surface, right? You take a line which is 1 0 0 one this same line, and you rotate it around the z axis. What you will get it? You understand my question?
Cylinder.
You will get a cylinder, right?
Mm.
So now actually what we are going to do is, so here also we have a circle and we have this open lines are there, right? Because I removed 0 now, I'll have a lot of these rays are there, right? And these rays are as many as whatever lines you can do it here. So here, so what is this actually? So can you write a homeomorphism so that each of this line will get a bigger like R? Can you do that? See, this is a line, this will be homeomorphic to line 0, 1, right? Because you can always push it here and you will get a, its length is actually 0, 1, right? But its location is somewhere else. Can you give a
1
homeomorphy?
by Z.
Maybe using some 10 function.
Yeah, actually, see, whatever Devi is also telling, you can use that, or tan function is also there, right? So I think what is that actually? Tan T, is it? tan inverse of something it is, probably pi minus t or something. Okay, just to see what is this. So this function will give me a homeomorphism from the 0, 1 to r, and then actually you have to do little intelligently how actually you have to write these coordinates. Okay, so that I'm leaving this, we will discuss it in tutorial. Okay, so what you do is, so essentially what we are trying to do is, suppose you have a hole, you are putting your hand inside that hole and making that hole as a cylinder. Okay, that's what. So once you have a, see, we don't need to give a entire infinite cylinder. Even if you give it to whatever cylinder which is a finite cylinder of length 1, then also I can always stretch it to the infinity, right? So that is what we are trying to do is, so this I'll leave it as a for you as an exercise. Okay, I'll give you an idea and just try to expand it. Okay, try to write it down. Okay, so that is about the cylinder. And similarly for sphere, can you write down, I'll leave that as also a tutorial problem, that if you can take a spherical coordinates and write it down, how sphere can be covered by spherical coordinates. Okay, but again for sphere also you have to do this, what, I mean, you have to do some kind of a, you have to rotate your patch so that you can cover the entire sphere using spherical coordinate. But for sphere, actually, I have another coordinate things that I'm going to discuss it now. Okay. So far, is it okay for why cylinder is surface? Is that clear to all of you?
Yes,
Why
ma'am.
cylinder is surface
Yes,
is
ma'am.
clear to all of you? Okay, good. So similarly, now let us go to a unit sphere. What happens to your unit sphere? So in case of unit sphere, there are a lot of different surface patches is there. Have you heard of stereographic projection?
Yes, ma'am.
Stereographic projection, right? So
Yes, ma'am.
stereographic projection, yeah. So stereographic projection is there. Another is actually cylindrical coordinates are there. So both of them will give you a surface patches, and I'll give you a one more surface patch which is actually much more easier than all these things. Okay. So what is that surface patches? What we are going to do is how actually our sphere looks like. Let me actually draw here. So this is okay. So sphere is like this, right? Like a ball. So what we are going to do is, this is my actually x, y, and z axis. So let us look at actually the z axis first. So this upper part of z axis. So if I take this upper part of z axis, means positive. So here actually what I'm looking at is, so I'm looking at all the points x, y, z, so that z is strictly greater than 0. Okay, so it is above xy plane. Okay, so this is a positive part of my z axis. So now actually, so can you give, so is this open? Is this clear to all of you why this is open? Inside, so this is, okay, so this is points on the sphere. So do you know why this is open? Can you tell me why this is open? Open inside the...
Yes, ma'am. It is the inverse image of the set R2 cross 0, infinity. Open interval 0.
Okay, okay, fine, but I don't want that. Can you give me a subspace topology with respect to subspace topology?
Ma'am, it is
So can
intersection
you...
with upper half portion.
Right, exactly. So that's what I wanted. Very good, actually. You take a R cross R, and then you take a cross product with a 0 to infinity. And then actually, so this will be what actually this not a plane, sorry, upper space, this entire whole of these things. And then you take intersection with S2. So this is a open. We know this is a clearly open inside R3. So this is going to be open. Is this okay?
Yes, ma'am.
Okay, just try to, it is, I mean, your answer is also correct, but then in that case, you have to also say that that map is homeomorphism, whichever map you are giving, right? Anything is okay, actually, it's fine. It is precisely the same only. Sorry, open in R3, this is okay. Right. So this is an open subset. And once I have this open subset, now can you give me a homeomorphism? So which open subset I'll use to give a homeomorphism here? So here actually what we are going to do is, we can always, if you project, suppose all these points, where what image you will get it? Just a project. So here actually, I'm going to project it on x comma y. So I'm just leaving z out. What you will get it? So I'm doing this projection map. Oh, I should call it sigma because we have a sigma as a notation. Where it will go, can you tell me? This is inside R2, that is correct, but can you tell me what condition I'll get it here?
Square plus y square is less than 1.
Yeah, less means strictly less than, right? X square plus y square will be strictly less than 1 because z is positive, right? So because of that, x square plus y square will be strictly less than 1. So what is this actually? This is open disk, right? And we know that, so this is our open disk inside R2. And now can you give this map sigma? Can you give this map sigma from this open disk to sphere? I mean that open, this I've denoted it by Z plus. Suppose if I xy here, how you will send it?
X comma y comma square root of 1 minus x square minus y square.
Very good. So we will going to send it like this. And what is the sigma inverse is? Just a projection, which I wrote already, right? Sigma inverse. But now actually, see, once we have a sigma inverse, then it is going to be a, I'm not proving all these things, but you can, this map is a clearly continuous map, right? I mean, there is no problem about that, because when you are taking a square root, we are taking a positive square root. So we are fixing that. And this is not going to be negative because we know that x square plus y square is less than 1, right? Another thing we know that x square plus y square, they are strictly less than 1. So this is going to be strictly greater than 0. Always remember that you should also check that it goes inside uz plus. So in uz plus, what we need is we need z coordinate to be strictly greater than 0. Okay. So then actually this will form. So now actually whatever, so this map, let me write it as a sigma z plus. This is going to be a surface patch. Are you convinced by this? This is going to be one of the surface patch. Are you convinced by this?
Yes, ma'am.
But this is certainly not enough. So what you have to do is to cover this sphere, you need another surface patch also. Na? So what is that surface patch is? Now what you can do is actually we can go below, right? So this part I went up. I can actually go from below, right? So what will be that set will be? So here z is strictly greater than 0. I can take z is strictly less than 0. Okay. And in that case, what will be this map is? This map has to be minus sign, minus square root of 1 minus x square minus y square. But is this going to be okay, or do you need something more than this? Will this cover the entire sphere?
No, ma'am.
See, the 1 unit 1 circle.
Yes, that is correct, Srinanda. So the things which are in the xy plane, which is that greater circle, that will remain, right? So for that, what you do is, but see, we can use as many as that of a surface patches. So what I can do is, I can actually take a 6 patches, which is this ux plus ux minus uy plus uy minus and so on. Okay, so that will cover my entire sphere. I think my time is up, and you have some other classes, right, after this?
Yes, actually. There is a tute after
Yeah. Sorry?
There is a tute after 15 minutes.
Okay. So can I just take another 2-3 minutes to tell
Yeah,
this
yeah.
circuit? I'll just take that and then I'll stop. Then
Yeah.
at least these lecture notes will be completed. Okay. So
Great.
so far what I have done is I have given you three surfaces, which are surfaces, but I should give you an example which is non-surfaces also. Okay. So for that, actually example is circular cone. So I'll just explain it to you and I'll share my notes to you so that you can read the details. Okay. So for example, so what is actually equation of this cone? Can you tell me? It is x square plus y square plus z square is equal to, no, sorry, what is that actually?
Equals to
This is
Z
equal
square.
to Z square. Yes, right. So if you take actually zeros of this, then what we get it actually this cylinder, sorry, this cone we get it, right? Right. And this is, so can you tell me why this is not a cone? What is your guess? I mean, where will be a problem? Just tell me, then we will deal with that.
Around
So which point is?
the pinch point.
Point
Right, very good.
intersection.
Right. So this is that pinch point. Now, what is that pinch point? Actually, when you have this equation is 0, 0, 0, right? So 0, 0, 0 is a problem. But why it is a problem? Can you guess actually? Can you, I mean, see, we have to prove it that it is not a, so can you tell me what will be a problem? Then we can actually expand it. So can I make it anytime this kind of thing as a what you call surface, or okay, can you tell me if I give you, forget about this for 2 dimension, 1 dimension, suppose if I have this cross line, what is the problem? Can you tell that is this homeomorphic to open subset of R anytime?
No, ma'am.
No.
Why? What is the reason?
Around the crossing
Not
point.
connected.
Yes, yes. Around the crossing point, if we take a neighborhood, then if we delete the crossing point, then there will be 4 connected components, whereas in R2 there is maximum 2 connected components.
Right, very good. So what we know about actually homeomorphism is connected component remain as a connected component. So those kind of things we call it as a topological invariant, right? So same way, suppose if I take a cone and if I remove this vertex from here, what will happen is, suppose if I remove the vertex from the, remove the vertex from the cone, will you get a one, is it a connected?
No, ma'am.
No.
No, it is
No,
two
ma'am.
disjoint.
It will have a 2
disconnected
open
components.
disk, you will get it, right? So exactly that is what we have to write it in the proof of when you are proving the that this circular what is that cone is not a surface. Okay, so what we are going to do is ki, suppose if there is a surface patch from you to this whatever to some sigma of no, what let me write it, S intersection S intersection with a W, such that this origin 0, 0, 0 is belongs to this patch, then what you can do is you can actually restrict this sigma to u minus that point, which will be, suppose P is there, such that sigma of P is equal to 0, 0, 0. So what you do is you remove from this open neighborhood, open set that point and go to S union minus 0, 0, 0. So here you will have a two path components or connected component, anything is okay here, and here you will have only single one. So because of, so that will give me a contradiction that this is a cone. So that explanation I wrote it here, so if you read it you will able to understand it. Okay, so I don't want to extend my time more, so I'll stop now. And if you have any doubts, I'm here. Otherwise, you can take a rest. Actually, I think you will have a next tutorial soon. So I'll stop now my lecture. But I'm here.